Okay, now before we get into the MPLS content for the day, we're going to spend a couple minutes talking about integrated system to integrated system routing. Now, those of you that took the routing and switching exam a few years back, this would have been in the scope for you. The current exam content does not have IS-to-IS as part of the blueprint, so we're going to spend a couple minutes to go over it. So whether you are familiar with it or not, we'll talk about just some general principles of it and then go through some basic configuration examples. Now, as Brian Dennis mentioned earlier, it is listed on the blueprint under the PE to CE routing protocols, but based on the hardware platforms that are used in the exam and the iOS versions, it's not actually supported for PE to CE routing. It's only under a 12.0S, one of the newest 12.0S trains. IS-to-IS is a PE-CE protocol. But the majority of places that we are going to see it is inside the service provider core. Okay, IS-to-IS means intermediate system to intermediate system, which simply means router to router communication. So it's an interior gateway routing protocol. Now, it is a link state protocol like OSPF, and it's actually the precursor to OSPF. Now, one of the main advantages of using this for service provider networks is that we can design our network in a very flat fashion where we don't need to worry about hierarchical OSPF designs in order to get the network to scale. So basically, we can go ahead and just enable IS-to-IS everywhere, and it's going to be fine. Now, one of the key points that we need to keep in mind with IS-to-IS is that it is not natively an IP protocol. IS-to-IS is actually part of the CLNS stack, which is the Connectionless Network protocol stack. Now, we are not going to be dealing with the legacy CLNS protocols, which would be CLNP and CMNP. Those are the precursors to the TCP and the UDP protocols of the TCP/IP stack. But what we are going to be dealing with is integrated IS-to-IS, which is the IP extensions to IS-to-IS in order to route IP version 4 packets. Okay, there's also an extension to route IP version 6, but in our case, IP version 6 is not yet part of the service provider blueprint. So we're just going to look at it within the case of IP version 4. Now, in order to configure IS-to-IS, first thing we're going to do is enable the process globally. So we say router IS-IS and give it a locally significant process ID. So just like OSPF, you can run multiple processes, and then based on what you configure on the interface, you're determining what process is running on that interface. So we configure the process, then we're going to define a network entity title address, a net address. Okay, this net address is going to be in the ISO NSAP addressing format, which basically means it's a 20-byte address that is in hexadecimal format. Okay, if you look at the actual ISO NSAP standard format, it shows a bunch of different hierarchy that you need to use for the net address, but that was only significant when you were actually routing the CLNS stack. When we're dealing with IS-to-IS for IP, basically it's going to be made up of 3 portions. You have an area address, you have a system ID, and an end selector. The area is not like in OSPF when we're talking about an area. It's going to determine what neighbors you can be adjacent with. Now, the system ID is going to be like your router ID inside the area. So this portion here, the system ID, that's going to be unique. And the end selector is always going to be 0. Okay, so what you should see with an IS-to-IS address, it's always going to start with 1 byte, and it's always going to end with 1 byte. If you put it in a different format into the command line, you'll see it's going to show up as an odd output in the running configuration, and sometimes it's going to give you an error message that that is not a valid format. So it's always going to start with 2 digits in hex, and it's going to end with 2 digits in hex. Okay, now in IS-to-IS, unlike OSPF areas, we are going to be dealing with different levels of adjacency in IS-to-IS. Okay, we have 2 levels. We have level 1 adjacency and level 2 adjacency. Now, when we configure the protocol on the command line, the routers are all going to be running in level 1, level 2 mode, which means they're going to form both adjacencies on any interface we enable IS-to-IS on, and they're going to have separate link state protocol databases for each of these adjacencies. Now, if you're trying to get a protocol to scale, it's not really a good idea to keep dual adjacency databases for the same type of information. Okay, so if we enable IS-IS everywhere and leave it as level 1, level 2, you're going to have duplicate information in the level 1 database as the same as you have in the level 2 database. Now, the level 1 routing is going to be like intra-area routing, similar to intra-area routing in OSPF. If you are in IS-IS level 1, you're going to see routes in your own area, so you're going to see intra-area routes. You'll see a default route out to the area border router, which is going to be called the L1, L2 router, and redistribution is allowed into the area. So if you compare it to OSPF, it's similar to the not-so-totally stubby area in OSPF, where you see routes in your own area, you see a default route out for everything else, but you are allowed to redistribute into the area. Now, IS-IS level 2, this is going to be synonymous to area 0 in OSPF. Okay, so level 2 must be contiguous throughout the IS-IS domain, and Cisco's implementation does not support virtual links. Okay, so we need to make sure that the level 2 adjacencies are contiguous. Now, within the scope of the service provider exam, this is not going to be that big of an issue because we're trying to look at better design networks as opposed to routing and switching, where we're looking at corner case scenarios and odd configurations just to test your knowledge of the protocols. But when we look at the core routing in the service provider network, typically we would see either flat OSPF area 0 or IS-IS level 2 just to perform basic transportation between the end-to-end devices in the network. So basically, from a core perspective, as long as you understand how the basic adjacency levels work, how to enable it on the interface, then you should be good to go with IS-IS. Okay, so level 2, again, that's like OSPF area 0. Level 1 is going to be like a not-so-totally stubby area. Now, to connect these levels, we're going to have a level 1, level 2 router, which is like an area border router in OSPF. So this is going to be our exit point from the level 1 network to the level 2 network. Okay, the level 1, level 2 router is going to inject a default route into the level 1 domain. Okay, so the L1, L2 router, that's going to be injecting a default into the level 1. Technically, it is not originating the prefix 0.0.0.0/0. What it's going to do, and we'll see this when we get to the command line, in the link state database, it's going to be setting the attached bit on its LSAs, letting the devices in the level 1 area know, or the level 1 domain, I should say, in the level 1 domain know that it has an attachment out to the level 2 domain. Okay, now, in order to form adjacency in IS-IS, we need to take into consideration that it is not an IP protocol. Okay, so this means that we need to make sure that we have transport for the CLNS stack first. Now, on broadcast medias like Ethernet or point-to-point links like PPP or HDLC or point-to-point interfaces in frame relay and ATM, that's not going to be an issue. Because with Ethernet, layer 3 to layer 2 resolution is going to be automatic. With the point-to-point medias, it's not going to be required because there's only one destination on the other side of the link. But with multi-point non-broadcast medias, so if we had a main interface in frame relay or a main interface in ATM doing PVC configuration, then we would have to do static resolution for the CLNS stack. And we'll see this when we go ahead and do an example of IS-IS on the command line. Now, the level of adjacency must match on the interfaces in order for the routers to become adjacent. Okay, there's two ways we can control the level. We can do it either under the process with the IS type command or under the interface with the IS-IS circuit type command. And as you can assume, if you do it globally under the process, that's going to affect all global interfaces. If you do it under the particular interface, it is specific just to that individual link. Okay, now there's only two network types in IS-IS. Any multi-point interface, it's going to be the network type broadcast. Any point-to-point interface is going to be the network type point-to-point. Okay, so like in OSPF, if you have a mismatch, you can go ahead and go on the interface and say IP OSPF network point-to-point in order to match up the adjacencies. Okay, but again, in service provider designs, this is typically not an issue because the majority of the time we are going to be using point-to-point links to connect the devices. And now the broadcast network type, like OSPF, it does have a designated intermediate system as opposed to a designated router and backup designated router to distribute the link state packets on the broadcast media. So when you look at the show CLNS IS neighbors, and we'll take a look at this on the command line, you can see that everyone is going to be adjacent with the designated intermediate system, and the DIS is responsible for sending out the LSAs to the rest of the devices on the segment. Okay, so the election process is similar to OSPF. We're going to be using a router ID and a priority in order to determine where or how the election process works. Okay, with IS to IS, we're using the system ID instead of the router ID, so that's based off of the net address. And the priority, we can go ahead and configure that at the interface level, and a higher priority is going to be better for IS to IS. Okay, so when we're looking at the show commands for IS to IS, you need to keep in mind again that it is not an IP protocol, so the show commands are going to be subcommands of CLNS show commands and IS to IS show commands. So when we go to check the adjacency status, we're going to look at the show CLNS IS neighbors or show IS neighbor output. Okay, like we can check the OSPF database, we could say show IS to IS database or the detail to see what LSAs we're learning from which specific devices. Okay, this would also tell us who is going to be the designated intermediate system on a particular segment. If you're having trouble forming adjacency, you can take a look at the debug IS adjacency packet to see what type of issues are coming into play. So like OSPF, we have things like the MTU could be an issue with IS to IS. And like OSPF, you can go under the IS to IS process and say, we want to ignore the MTU as part of the adjacency negotiation. Okay, so if you understand the logic of how OSPF works as a link state protocol, then that is going to translate directly to IS to IS. They actually use the same algorithm for computing the computing SPF. So if we take a look at our diagram here, we have a basic example of an IS to IS network, and we'll go ahead and set this up on the command line. If you take a look in the notes box in the bottom left, you can see a link to the topology PDF that we're going to be using throughout the week. So depending on what technology we're looking at, we may be using the entire diagram, we may be using a subset of it. So if you want to print out a bunch of copies of that, feel free to do that, and then you can just draw on there to go ahead and match up with what we're doing here. So in this case, what we have routers 1, 2, 4, and 5. They are going to make up the level 2 domain in IS to IS. So we're going to have level 2 adjacencies on the ATM link, the Framula link, and then this Ethernet link between router 2 and router 4. Then on this link between router 1 and 3, we'll have level 1 adjacency, and level 1 adjacency between router 5 and router 6. Based on the fact that routers 1 and 5 have both level 1 adjacency and level 2 adjacency, that is going to make them the level 1, level 2 routers. Okay, so when router 3 and 6 look in their routing tables, the only thing that they should see is going to be a default route out to these particular neighbors. Okay, so let's go ahead and bring up the command line. We'll go through this basic configuration and show some show commands, and then we'll move on to our main topic for this afternoon, which is going to be MPLS. Okay, so everybody should be able to see my secure CRT screen. So what we're going to do, We'll go ahead and start at the level 2 core. So we'll start on router 2 and router 4, and we'll go ahead and assign their net addresses. Then we'll go ahead and enable ISDIS on those links. Okay, so the first thing we're going to do under the global process, we'll go ahead and enable ISDIS and define its network entity title address. Okay, so unless this is specified in the scenario, this is going to be fairly arbitrary. So if we look at the slides there, we could see what the area it's supposed to be in, and the area is going to be anything to the left of the system ID. Okay, so we have a system ID of all zeros and then a 2, and the end selector is 0 here. So anything to the left of these bytes, that is going to be the area address, anything up to 20 bytes. Okay, once we have it enabled, this router is going to be running both level 1 and level 2. Now in this case, if we want to form only level 2 adjacencies, we have two different options. We can go to the interface and specify for that particular interface what the level is, or globally we can say that the IS type is going to be level 2 for all interfaces. Okay, so if we go to the interface here, we'll say IP router ISIS. So this is going to be on the Ethernet and on the ATM link. If we look at our ATM configuration here, we can see we have just basic static PVC configuration on a multi-point interface, so we are doing manual layer 3 to layer 2 resolution. Okay, so if we test our connectivity here, we should have reachability over to router 1 and over to router 4. Okay, so at these interfaces, on the ATM we'll say IP router ISIS, and we have that on the Ethernet as well. Okay, so we'll go over to router 4 here and basically do the same thing. We'll enable the ISIS process, define the net address. We'll say this is going to be only a level 2 process. And we'll enable ISDIS on the interfaces. And likewise, if we look at our serial interface here running frame relay, we can see this is a multi-point interface that's doing static layer 3 to layer 2 resolution. Now, if we go ahead and look at the adjacency status between these neighbors, if we say show CLNS IS neighbors, we can see we are adjacent with router 2 on the Ethernet interface. We can see the type of adjacency is level 2, and the circuit ID is rack1r2.01. This means that for this link, router 2 is the designated intermediate system. So it's like the DR and OSPF. Router 2 is responsible for distributing LSAs. Now in this case, since there's only 2 neighbors, it really doesn't make a difference who the DR is. So unless there's some specific requirement in the exam, we're just going to establish basic routing connectivity. Now, if we look at the debug, so let me go back to global config before we do this. Now, one recommendation I'm going to make in the lab exam when you're debugging, and Brian mentioned this a little bit when he was talking about PPP, you want to make sure to avoid any case where you can possibly lock yourself out of the command line. Is if you lock yourself out, worst case scenario, you're not going to be able to get back in at all during the exam, but at a minimum, you're going to lose time configuring, whether you have to reboot the device and do password recovery, or if you didn't save your config soon enough, then you're going to lose some time in configuring. One of the things you can do to avoid this is that instead of logging to the console, we'll go ahead and log to the buffer. So in global config, we'll say logging buffered, and we'll say no logging console. Okay, then we're going to debug ISIS adjacency packets. Okay, so we'll let the buffer fill up with a couple of those, and then we're going to look at the show log output. Okay, now what we should see here when we look at this output is that we're sending level 2 hellos. We're sending level 2 hellos out our Ethernet interface, and we're receiving level 2 hellos. So we receive level 2 hellos on Ethernet. We're sending them on Ethernet. And then we're sending them out the serial interface. But what it's telling us, encapsulation has failed for a level 2 hello being sent out the serial interface. Okay, anytime you see the encapsulation failed message, whether it's in a debug IP packet output, whether it's this debug, which is debug IS-IS adjacency, or debug frame relay packet, what that means is that when you go to send the packet to the interface, you don't know what layer 2 address to associate the packet with for transmission. So basically what it's telling us here is that we're trying to send this packet out the interface, but we do not have a mapping for that particular protocol stack. Because if we look at the interface, we can see we have a mapping for IP, but since IS-IS is not part of the IP stack, this command here, frame relay map IP, is not going to provide transport for it. So what we need to do in addition to this is that we're going to say we also need to map CLNS, which is also going to resolve the circuit 405. And we're going to include the broadcast keyword there. A same case is going to be on router 2 on the ATM link. Okay, so if we debug IS-IS adjacency, it's going to say we're sending the IS-IS packets out the ATM link, but encapsulation is failing. So on this interface, ATM30, under PVC 201, we're going to need to put a protocol mapping for CLNS. In this particular version, this protocol resolution is going to depend on what platform and what specific train of iOS you're running. In this case, it's saying we have 3 different options for the CLNS stack. CLNS refers to the actual routed protocols like CMNP and CLNP. What we're looking at specifically is intermediate system to intermediate system, which uses a different layer 2 protocol code than these other ones do. So it's saying do not map the entire CLNS stack, just IS to IS in this case. Okay, so when we configure this on router 1, we're going to have to do the same thing back on the other end of the link. Okay, so next we'll go up to router 1 and router 5, who are our other level 2 routers, and they are also connected to the level 1 domain. Okay, actually, before we do that, let's go ahead and on router 2 and 4, let's advertise their loopback interfaces into IS to IS. Okay, there's 2 ways we can do this. We can go directly under the loopback and say IP router IS-IS. Or under the IS-IS process, we can say passive interface loopback 0. Okay, so they're effectively going to do the same thing, which is injecting the prefix into the IS-IS database. But when we use the passive interface command, we can't form adjacency out that link. But in this case, since it's a loopback interface, we're not going to be forming adjacency with anyone. So whether you use the router IP router IS-IS or the passive interface command, it's going to have the same effect here. Okay, so next let's go over to router 5. We'll define its IS-IS process and then enable adjacency with routers 4 and 6. Okay, so we define the IS-IS process, configure the net address, and then enable IS to IS on the both of the interfaces. Now, if we look at the debug output here, what we would see is that we're sending both level 1 and level 2 adjacencies out both of these interfaces. Now, for the link over to router 4, we only want to form level 2 adjacency. So on the serial link, we're going to say that the ISIS circuit type for this link is going to be level 2 only. Then the Ethernet link over to router 6, that's going to be level 1 only. And additionally, just like on router 4, if we look at the frame unit configuration here, under this interface, we're going to need to provide transport for CLNS. So we'll say frame unit map CLNS, out circuit 504. Okay, so we can see we're adjacent with router 4 there, and if we look at the routing table, show IP route ISIS, we can see we have the loopbacks of routers 2 and 4, and then the 2 transit links between them. So we have the link between 2 and 4, and then the link between 1 and 4. Okay, then on router 6, we'll go ahead and enable the level 1 process. Now in this case, whatever area that router 5 is in, router 6 is also going to be in, because that is a requirement of the level 1 adjacency. Okay, you can only be level 1 adjacent with people that are in your own area. And the area, again, is defined by anything to the left of the end selector and the system ID. So in this case, the area is 49.0016 in hex. Okay, so we'll enable ISIS. We'll say globally under the process, this is going to be level 1 only. Okay, then under our Ethernet, we'll say IP router ISIS, and on our loopback as well. So if we look on router 5, now we can see that we're adjacent with both router 4 and 6, and the adjacency with router 4 is a level 2 adjacency, while the adjacency with 6 is a level 1 adjacency. So if we look at router 6's routing table, what we should see is that the only thing it has is other routes within the level 1 domain, okay, which is router 5's loopback in this case, and then a default route out to the level 1, level 2 router, which is router 5. Now, if we look at the database, if we say show ISIS database detail, what we're going to see here is that router 5 is setting the attached bit in the database. So router 5 is telling router 6, we are level 1 adjacent, and I have access to a level 2 domain. So I'm setting the attached bit, which is going to make you use me as a default destination. So technically, it's router 6 installing the default route, and router 5 forces it to do that based on the attached bit being set in the link state database. Okay, so if we go ahead and build the adjacency on router 1 and router 3, we're going to see the exact same thing. We're going to see router 3 is using router 1 as a default destination, and then everyone inside the level 2 domain. So if we go over to router 2 and we show IP route ISIS, we'll see that router 2, anyone in the level 2 domain is going to see all the routes throughout the entire network. So it's similar to OSPF Area 0 in the fact that it is going to see every link state in the entire network. The level 1 domains are going to be they're going to have a smaller view, which is just the routes within their own domain, and then a default route out to the level 2 domain. Okay, so what you'll see, the Technology Lab series that is going to accompany this class in the workbook, there will be a number of examples in there for IS-to-IS, but the majority of the time what you're going to see it is going to be that it's for the core of the network in the service provider. So again, with the current versions, we're not going to be running it as a PE to CE protocol. We're just going to be running it between the provider routers. Okay, any questions on IS to IS before we get into MPLS? Okay, so this afternoon what we're going to cover is just a basic overview of what MPLS is. We'll take a look at some basic MPLS examples and do some show commands and troubleshooting on the command line. And the stuff that we're seeing here is going to be the basis for the transport for all of the technologies that we're going to put on top of this. Okay, so we need to make sure we understand how the label distribution process works and how to troubleshoot and verify what the label mappings are going to be as traffic is moving throughout the network. Now, MPLS is going to stand for multi-protocol label switching. You can see throughout the slides there'll be links to some RFCs. So after class, if you want to go back through and read those, there's a lot of good information that you can find in the RFCs, especially for these service provider technologies. So a lot of the times when you're trying to get really technical details on this stuff, you really need to go into the RFCs because that's what everyone's implementation is going to be based off of. Now, MPLS is the evolution of what Cisco used to call tag switching. So you'll see terms that we're using in terms that are used on the command line. Anytime we're talking about a tag or a label, those terms are going to be basically the same. So the protocols that we're using to distribute these labels, typically we're going to be using either tag distribution protocol or label distribution protocol. Let's see it in here. We'll come back to that. So we're going to be using either TDP or LDP to distribute those, but they're basically going to accomplish the same thing. And now what we're going to see with MPLS, the reason it's called multi-protocol is that the payload it can carry is going to be a variety of different protocols. It can be layer 3 protocols like IP version 4 or IP version 6, but you can also tunnel layer 2 protocols like Ethernet, HDLC, PPP, that type of stuff over the MPLS network. Now, the majority of focus that we're going to be doing is going to be layer 3 VPNs or layer 3 MPLS through IP version 4. Okay, there is an emerging standard for transporting IP version 6 over MPLS, but as of the current blueprint, IP version 6 is not part of the service provider exam. So probably 95% of the stuff we're going to be looking at is going to be IP version 4 over MPLS. And now we call it label switching because MPLS is going to use a process that's similar to how ATM uses the VPI and VCI value of an ATM cell in order to determine what interface it's going to go out. Now, the basic logic of MPLS says that when you receive an MPLS packet in an interface, you're going to look at what the label associated with that packet is. You take this label and you correspond it with a label switching table, which is called, we're going to see it's called the label forwarding information base. And based on the incoming label on the incoming interface, it's going to show us what interface it should go out and what the outgoing label number should be. So basically, instead of looking at the IP header to move the traffic, we're now going to be looking at the MPLS header. So if it comes in interface 1 with label 1, well, we can send it out interface 2 with label 2. Okay, and these label values, these are going to be locally significant between the two neighbors that are using them. So depending on what interface it's coming in on, you can reuse the label numbers on different interfaces. Okay, this process is going to be pretty much automatic. So the only thing we need to do is enable MPLS, and then the labels are automatically going to be distributed for the destinations that we are trying to reach. Now, the main reason that we want to use MPLS in a service provider network is that it's going to save resources in the service provider core, and it's going to allow us to use additional features for our customers, like providing transparent layer 3 VPN service. Now, traditionally, when we talk about VPNs tomorrow, we're going to talk about the difference between an overlay VPN model and a peer-to-peer VPN model. So traditionally with VPNs, if you're a customer and you have a site in New York and you have a site in Los Angeles, if you want a private network between these sites, you're going to purchase something like Frame Relay or ATM, depending on what your access speed you want into the network is going to be. Now, the problem with this from the service provider's perspective is that you're going to need to have that infrastructure end-to-end between those two sites in order to provide that layer 2 transport between the customers. Now, MPLS makes this a lot easier because it's independent of whatever media it's running over, and you can transport it between providers. You can transport it within your own network for just one provider, and it's going to make provisioning these circuits between the customer sites a lot easier. Okay, so what we're going to see is that when we're running MPLS, we're going to see that devices in the service provider transit path don't necessarily need to run BGP. So we're going to see this principle that we're going to have a BGP-free core, so every device in the transit path is not going to need to carry the full internet routing table or the customer routing tables. Because as it is now, the full global internet table is above 200,000 routes. So if you're looking for devices in the transit path that have very fast forwarding capabilities, you don't want them to have to look through a table of 200,000 routes every time they want to switch a packet between interfaces. So MPLS is going to greatly reduce the number of entries that we have in our forwarding table by using this principle of tunneling the traffic between individual sites. Now, another main advantage we're going to talk about tomorrow is traffic engineering through MPLS, which is going to allow us either dynamically or manually to choose the path that we want to route through the network. Okay, so MPLS traffic engineering is going to reintroduce the notion of source routing through the network. So if we are at point A and we're trying to get to point B, point A can explicitly say, I want to use this path throughout the network in order to get there. So the source of the traffic is determining which route it wants to use through the network. Okay, so some advantages of doing this: we can distribute bandwidth over links that are underutilized better so than our regular internal or interior gateway routing protocols can do. So protocols like OSPF and IS-to-IS, which are typically used in the service provider core, they don't do a lot of unequal cost load balancing without a lot of complex changing the cost of links and making links that are lower bandwidth basically look the same as higher bandwidth. So if we have OC48 links and OC192 links, OSPF and IS-to-IS are going to choose to go over the OC192 first. That's going to be based on the IGB metric of the link. But if the OC192 is saturated and we have OC48 sitting right next to it underutilized, then traffic engineering we can go ahead in there and manually specify what traffic can go over those underutilized links. Another advantage of it is that we can provide basically sub-second convergence for links between devices. And that's going to be based on a feature called Fast Reroute with MPLS Traffic Engineering. Now, I believe it is listed on the blueprint for the SP exam, Fast Reroute. We'll talk about it briefly, but as of now, with the current versions they're running and the current platforms, you can't actually configure it on any of the routers. A configuration of it, anyways, is pretty straightforward. It's only a couple commands on the tunnel interfaces, but Fast Reroute, it's good to know for your practical implementation of this stuff, but it's unlikely that you're going to see it in the exam until they go ahead and upgrade either the versions or the platforms again in the future. Okay, now the actual header inside MPLS is going to be made up of 4 different fields. The main one that we're going to be looking at is going to be the label. Okay, so the label is going to determine when the packet comes in, what interface it's going to go out, and what outgoing label it's going to have. Okay, we also have a 3-bit class of service value that's called the MPLS experimental bits. And when we get to quality of service, we're going to see how we can take customer policies, whether they are encoded with IP precedence or DSCP, and we can map those to the MPLS experimental bits in order to change the per-hop behavior of traffic as it's going through the service provider network. And now, since the experimental bits are only 3 bits, that's going to tell us that we only have 8 possible values for this class of service. Okay, so it's not going to be a very granular policy that we can implement, but it at least gives us some field to use to color traffic for different policies as it's transiting the service provider network. Okay, the S bit in the label is going to tell the device that this is the bottom label in the label stack. And when we look at MPLS VPNs tomorrow, we'll go into more detail on why the label stack is going to be significant. Okay, one of the big advantages of MPLS is that there's no effective limit on how many times you can re-encapsulate a packet inside MPLS. So we can take an MPLS packet and then re-encapsulate it with another header and keep adding headers onto this to do different types of forwarding as we want it through the network. Okay, so we're going to use this label stack for applications like VPNs and for traffic engineering. Okay, now when a device receives an MPLS packet, it is only going to make its decision based on the topmost label in the stack. Okay, so you are always looking at what is the first MPLS label that is on this packet, and that is how you are determining what is going to go on with your forwarding policy. Okay, then the last part, you have a time to live, which is similar to the IP time to live. So if that expires, then you're going to drop the packets, basically to prevent traffic loops throughout the service provider network. Now, when we enable MPLS in the network, basically what we are going to be enabling is the process for the routers to talk to each other and bind different labels to different IP version 4 prefixes that they have installed in their routing tables. Okay, when you take an IP version 4 prefix and you bind it to a label, we are calling this a forwarding equivalency class. Okay, so an MPLS label that refers to an IPv4 prefix, we call it an FEC or a FEC. Okay, now the router is going to use, instead of using the routing table now to route traffic, it's going to look at the MPLS label forwarding information base, which is the LFIB, instead of the Cisco Express forwarding FIB or the regular IP routing table to move traffic. Okay, now this is going to be very important in our troubleshooting process and when we're going through different debugs throughout the week. You always need to think about when you are looking at traffic coming in or going out an interface. Is this going to be an MPLS label packet, or is this going to be a regular IP version 4 packet? That's going to determine what type of verification we can do on it, whether it's going to be looking at different counters from the show commands, or looking at debug packets to see what's going on with the traffic as it's coming in and going out. So if we are receiving an MPLS label packet in an interface, we cannot apply an IP-based debug to that packet, because the router is not looking at the underlying IP version 4 payload. It's looking at just the label that's on top of it. Okay, so again, what these labels are going to do is allow us to say that when we receive a packet, if it comes in interface 1 and has a label X, we're going to consult the label forwarding information base, which is going to be the label forwarding table. Label forwarding table tells us that if it came in with label X on interface 1, we're going to send it out interface 2, but we're going to switch the label and change it to Y. Okay, this is known as a label swap process. Okay, so when we're taking a label in and changing it with a different label as it's going out, that's going to be a swapping process. Okay, now there's a question here. Considering Ceph is enabled for both of them, what is faster, label switching or label or regular routing? Now, you will see in a lot of the resources that they say one of the advantages of running MPLS is better forwarding performance for it. But nowadays, with the ASIC-based platforms, it really doesn't make a difference. Now, if you're looking at something like a 2600 or 3600 and looking at that's forwarding capabilities, you may see a difference in performance versus label switching versus IP routing. But if you're looking at the actual service provider platforms, which would be like the GSRs or the CRS, the way the hardware architecture is, the forwarding speed from IP version 4 versus the labels is really not going to make that much of a difference. Okay, but one of the main advantages is going to be the amount of resources we're using. So the label table typically is going to take a lot less memory because we have a lot less entries in the label forwarding table as opposed to the BGP table. So for example, let's say we have a full routing table, full internet routing table. It's about 200,000 routes. If we were to equate this to MPLS labels, we may only have 10 or 20 exit points from our network. So in order to reach all 200,000 of those routes, we may only need 10 or 20 label entries to get there. So we're looking at a lookup of 200,000 possible lookups versus 20 different lookups. But the way the Ceph algorithm works, whether the lookup speed is going to be different, that's going to depend on the platform, but the real savings is going to be in the memory and the amount of resources that is dedicated to holding the actual table. And what a big concern of service providers is not necessarily just the forwarding speed, but how big is that platform going to scale? Because if you have multiple customers and you're receiving multiple BGP feeds between each of them, and you're sending those inside VPNs, let's say that you have 5 different VPNs, for example, that are transiting your network, and each of these VPN customers are using you for internet transit. So there's 200,000 routes in each of these. If every device in the transit path had to carry those full tables, then every device would have to have at least 1 million routes installed in its routing table. Okay, so when we look at how the MPLS tunneling process works, it gets around this by hiding all of the IPv4 packets from the transit network, and they're going to look at just these MPLS labels in order to move traffic between the interfaces. You know, a couple different terms real quick that we're going to be using throughout the week when we're talking about the roles of the devices. First off, we have a PE device, which is a provider edge router. This is also known as an LER, which is a label edge router. These are the devices that are facing the customer networks. Okay, so when we're talking about running a routing protocol between the service provider network and the customer network, we call that our PE to CE protocol because it's running between the provider edge and the customer edge. Now, the PE routers, they are going to be taking unlabeled packets from the customer and adding the MPLS stack onto them. Okay, this process is going to be called MPLS label imposition or the label push operation. Okay, there are some exceptions to this. We'll see when we look at some advanced scenarios with carrier supporting carrier later in the week. But as a general rule, the PE's job is to take traffic from a customer, put a label onto it, then go ahead and forward that into the service provider network. Okay, so the provider edge is actually going to be doing 2 lookups. It's going to be doing a regular IP routing lookup, and it's going to be also doing an MPLS lookup based on the forwarding table. Okay, once the PE router forwards it into the provider network, it's going to be forwarded to a P router, which is a provider router, or an LSR, which is a label switch router. Okay, these are the routers that have only provider-facing interfaces. So on all of their interfaces, they don't have customer networks on any of the interfaces. Okay, so they are only going to be used to switch MPLS labels between different provider routers or different provider edge routers. So the main savings that we're going to see when we look at the different resources that are being used on the networks is going to be on these PE routers, or excuse me, these P routers. The provider routers do not necessarily need to run BGP in order to provide BGP transport. Because instead of doing IPv4 lookups, they're going to be doing their lookups based on the MPLS label. Okay, so everything is going to be based on that label forwarding information base, the LFIB on the P routers. Okay, now we see the case here where we have routers 3, 1, 5, and 6. They are making up the MPLS network. Okay, they are connecting to 2 different customers. We have router 7 and we have router 8. Okay, now the first thing that's going to happen in the label switching process is that we're going to have our regular routing advertisement. Okay, so routing advertisement could either be via an IGP like OSPF or EHRP, RIP. It could be via BGP, or it could even be by static routing. Okay, so what happens, router 8 has network X that it knows. Okay, so this could be directly connected. It could be learning it from some other destination. It is advertising network X to router 6. It's saying, in order to get to network X, use my next hop .8. Okay, so that's the IP version 4 address that is assigned to router 8's interface there. So next, router 6 turns around and advertises this to router 5. It says to reach X, you're going to use .6. 5 passes it on. It says to router 1, in order to get there, you're going to use .5. 1 says to 3, you're going to use .1. 3 says you're going to use .3. So what we can see on a hop-by-hop basis, these devices forwarding decisions are independent of everyone else. So the next hop value is changing on a hop-by-hop basis. So router 7 says, I need to go to router 3. Router 3 says, I need to go to router 1, etc., etc. Okay, so this is going to be the first step in the MPLS process. We need to make sure that we have our underlying routing protocol that is going to provide transport for the network advertisement. So this is either going to be IGP or BGP. A next step inside the MPLS network, we are going to take this destination X and change it in to an MPLS forwarding equivalency class, an FEC. Okay, we do this by binding a label advertisement onto the routing advertisement. So in addition to router 6 saying, you're going to reach destination X via my IP address .6, it's also saying, you're going to reach X via label L1. Then router 5 says to router 1, you're going to reach X via label L2. And 1 passes it on, you're going to reach X via label L3. Okay, now the process that this label distribution occurs is going to be based on, it's going to start from the source, or actually it's actually going to start from the destination. It kind of gets confusing, the terms that you'll see used, because it depends on what perspective you're looking at the network. Okay, the downstream portion of the network is going to be defined as the final destination. So the final destination X, this is going to be the furthest downstream portion of the network. So the MPLS label distribution happens upstream away from the destination. Okay, so router 6 is telling router 5, this is the label that I want you to use in order to get to this destination X. 5 is saying, 5 is saying to 1, you're going to use label 2 if you want to get to X. And 1 says to 3, you're going to use label X if you, or you're going to use label L3 if you want to get to X. Okay, now once we have the IGP advertisement done or the BGP advertisement done, which is going to be the underlying routing, and we have the label distribution happening, now we can see what happens with the actual traffic flow. Router 7, which is a customer switch or a customer edge device, is going to send a regular IP version 4 packet onto router 3. A router 3 is the provider edge, so it is taking an IP version 4 packet and it is imposing the MPLS label. So it's saying take that payload, which is the IP version packet going to destination X, and slap the label L3 on top of it. Based on the MPLS forwarding information base, the LFIB, it's going to know that this needs to go out the interface towards router 1. And it should be using label L3 as it's going out to router 1. Now when router 1 receives this, it doesn't care what is inside the packet. It is not looking at all that this is an IP version 4 packet to X. The only thing it sees is that this packet came in, it had a label of L2. Router 1 looks at its forwarding information base and says, if it came in this interface from router 3 with a label of L2, or excuse me, a label of L3, it's looking at the packet coming in from router 3. It's saying if it came in from router 3 with a label of L3, change the label to L2 and send it out to router 5. I'm not going to look at what the payload is. So I don't care if it's an IP version 4 packet, it could be an Ethernet packet, could be an IP version 6 packet, doesn't matter. We're only looking at what the MPLS label is on the top of the packet. A router 5 is going to do the same thing. When it comes in as label L2, it says if it came in from router 1 with label L2, we'll send it out to router 6 with label L1. Okay, then finally, the last hop provider edge device, which is actually attached to the customer network, it is going to be doing an IP version 4 lookup. So it says the IP version 4 packet came in, it's going to destination X. Now I'm going to use my regular IP routing table to do this lookup. So either it's through static routing or IGP or BGP, then we go ahead and forward it out the interface there. Okay, but what we can see is significant about this label switching is that router 1 and router 5, they do not even need a route to get to destination X. The only thing that they need to know is what is the incoming label and what is the outgoing label in order to move traffic between router 3 and router 6. Okay, so they don't care what the IP version 4 destination is. The only thing that they know is the traffic is moving between router 3 and 6, and they're going to switch it based on the labels. They're not going to switch it, they're not going to route it based on the IP version 4 destinations. Okay, now there's 3 different operations that we can perform on an MPLS packet. They're called push, pop, and swap operations. Okay, these are going to be performed either by the provider edge or by the provider routers. A push operation means that it's adding a label onto the MPLS stack. Okay, this is called push or imposition. But anytime you see on the command line it's talking about imposition, it means that you're adding a label onto the label stack. A label swap operation, you're receiving a label packet, you're taking the topmost label off, and you're replacing it with a different value to go out a different interface. In the pop operation, you're taking the label off, and this is also known as label disposition. Okay, so if we look at the previous example, router 3 is going to be performing the push operation. A router 3 is performing the push. So it's taking the IP version 4 packet and it's adding the MPLS header onto it. A router 1 and router 5, they're receiving the packet in one interface, changing the label value, and sending it out another interface. They are performing the swap operation. Now router 6, it's receiving the MPLS packet, taking the header off of it, and sending it out as an IP version 4 packet. So router 6 in this case is performing the pop operation. You know, what specific operation is going to happen? This is going to be determined based on the label forwarding information base. So when we look at this on the command line, we'll see either it's going to say the packet comes in unlabeled and we're going to label it, which means it would be a push operation. We can see an incoming label with a value and an outgoing label with a value. That's going to be the swap operation. Or we're going to see an incoming label value and an outgoing label of untagged, which means we are going to pop the top label. So we're going to take the label off of the stack. Okay, so same operation we're talking about. We can see router 3 here is pushing label 3 on. Router 1 is swapping label 3 with label 2. 5 is swapping label 2 with label 1. And then 6 is popping label 1 off in order for its final transmission onto router 8, which is the IP version 4 packet. Now the last example we were looking at, we saw that router 6 was doing 2 things. It was receiving a label packet in. It was doing a label lookup in the label forwarding information base. A router 6's forwarding table says that if it comes in with label L1, we need to take that label off. It takes the label off and it sees underneath that label packet we have an IP version 4 packet. So now what we need to do is do our regular IP version 4 routing lookup. So we look at either the CEF table or in the route caching table, or in the regular routing table, depending on what type of switching mechanism that we're doing. Okay, so we do that lookup, we see that packet needs to go out to router 8, so we go ahead and encapsulate it on that interface. So in this case, router 6 is actually performing two different lookups. It's performing the MPLS lookup, and it's performing its regular IP version 4 lookup. Now we can optimize this by a feature that's known as pin ultimate hop popping. And this is going to be on by default in Cisco IOS. So when we go ahead and configure this, we're going to see this is the default operation, that PHP is going to be enabled. Okay, the way that this works is that if we look at our first example, the way that the labels were advertised out. Okay, router 6 said to router 5, in order to get to destination X, I want you to use label L1. Then router 5 is propagating that further upstream. It's saying to get to destination X, you're going to use label L2. Now router 6 knows that it is the provider edge router for that destination. It is the one performing imposition, so anything coming from network X going into the service provider network. And it is performing disposition, so anything coming from the MPLS network towards the customer is going to be sent out untagged. Now we can optimize this by having router 6 tell router 5 that it is the last hop in the MPLS network for this particular destination. And the way it does this is by advertising a label saying that I am the implicit null destination for that particular forwarding equivalency class. Okay, so router 6 says to router 5, when you send me the packet, I do not want you to put a label onto the packet. I want you to send me a null labeled packet. Okay, so a null labeled packet is essentially a packet that does not have a label. So what we see here is that 6 is going to advertise implicit null, and we'll see this in the forwarding table when we go ahead and look at the command line. Router 5 is going to say X is via router 6. The outgoing label is implicit null. Now when we actually go and send the traffic throughout the network, router 3 is going to receive traffic from router 7. It is going to impose or push label 3 onto it. It's forwarded out to router 1. Router 1 is going to swap label 3 with label 2. It goes over to router 5, and when router 5 does a lookup, it sees that it is going out to router 6 via implicit null. So it is going to pop the top label, which is label 2, and it's going to send the unlabeled packet on to router 6. Okay, now when we look in MPLS VPNs, this operation is going to be very important based on how we are choosing to do our BGP peerings. So depending on what interface you choose to peer with via BGP, it can affect connectivity in the network. And it's going to be based on this penultimate hop popping operation. And we'll talk about that in more detail when we get to MPLS VPNs tomorrow. Okay, so this is actually going to be by default. Once you enable MPLS on the interfaces, this is automatically going to happen. So if traffic is going from router 7 to router 8, only routers 1 and router 5 are going to be switching the MPLS packets. Router 3 is going to be doing the imposition, and router 6 is going to see just a regular IP version 4 packet. Okay, now to enable MPLS in the network, basically what we need to do is enable a method for distributing these label mappings to the IP version 4 prefixes. Okay, this is going to be through a label distribution protocol. So a label distribution protocol is a general term that is describing the different methods, but one of the methods is called LDP, which is actually the label distribution protocol. So it gets kind of confusing the way they made the terms here. Okay, so we can distribute labels through LDP, which is the label distribution protocol, or Cisco's proprietary tag distribution protocol. Okay, TDP was the precursor to LDP, and it was used when MPLS was not standards based. Okay, it was based on Cisco's original implementation. Now, LDP and TDP, they are IGP based label distribution protocols. So they're going to be using the regular IP routing table, and they're only going to use entries that are installed via IGP. So this is going to be static routing, RIP, OSPF, IS-to-IS, EIGRP, etc. Okay, they're automatically going to take any IGP routes in the routing table and then bind labels to them and advertise them to the adjacent neighbors. Okay, another option we have is through multi-protocol BGP. Multi-protocol extensions to BGP, it's defined in this case in RFC 3107. It's called carrying label information in BGP version 4. You'll sometimes see this defined as, if you see BGP plus label. Okay, if you see the term BGP plus label, it means multi-protocol BGP for MPLS label distribution. Okay, the last one that we're going to see is through resource reservation protocol, and this is going to be used typically with MPLS traffic engineering. Brian Dennis is going to cover some examples where you can use RSVP without traffic engineering to directly advertise labels between neighbors. But typically this is going to be used with traffic engineering in order to advertise what are the available resources in the network, hence resource protocol, and to reserve bandwidth throughout the network. So we're advertising what resources are available, and then we're making network reservations to make sure that transit between two different destinations has enough available bandwidth in the network core. Okay, so today we're going to focus on LDP and TDP. Then when we get to MPLS VPNs, we'll talk about the multi-protocol BGP, and when we get to traffic engineering, we'll talk about RSVP in more detail. Okay, now the difference between TDP and LDP, they basically perform the same goal, which is taking an IGP route and advertising an MPLS label for it. The difference is that TDP is going to be Cisco proprietary, LDP is the open standard. And they also use different port numbers and transport addresses. So TDP is going to be using UDP broadcast support 711. LDP is going to be using UDP multicasts to the all multicast router address 224.0.0.2 using port 646. Okay, and if you forget these, what the ports are, what the destination address is, you can always look at the debug IP packet output on the router, and it'll show you, actually debug IP packet detail, we'll take a look at that. It'll show you what the destination address is, so whether it's broadcast or multicast, what the protocol is, so whether it is, well, the protocol in both cases is going to be UDP. What the port is going to be, so UDP 711 versus 646. Okay, so the first stage of LDP and TDP negotiation is that they're going to advertise themselves out through UDP. Okay, this is to discover neighbors that are directly attached on their segments. Once they discover a neighbor, they're going to go ahead and establish a TCP session between them. So the label advertisement is reliable because it's based on TCP. Okay, the actual TCP setup is going to be similar to how BGP works, where one of them is going to be the TCP server and one of them is going to be the TCP client. Okay, now the configuration of these protocols is very straightforward. It's basically two commands. Okay, first off, you enable Ceph globally. You say IPseph. Then at the interface, you say either MPLS IP or tag switching IP. Okay, both of those commands are going to do the same exact thing. It depends on what version of iOS you're running. You'll see sometimes that when you enter MPLS IP, it will show up as tag switching IP, or vice versa. Okay, so if you say tag switching IP, sometimes it'll show up as MPLS IP, and vice versa. Okay, but they're essentially doing the same thing. The actual command MPLS IP versus tag switching IP does not control what label protocol you are running. You use the interface level command or the global command, MPLS label protocol. That determines whether you are running LDP or TDP. You can actually run both of them on the same interface if you want to. So if you had an Ethernet interface to two routers, you could run LDP with one of them and then TDP with the other. Okay, now the defaults, you have to be careful because it depends on the iOS version. So you'll see some inconsistencies. When we look at this on the command line, we'll see it's different on the 7200s versus the 2600s versus the 3600s and versus the 3800s. So it depends on the platform and the specific version of code that you're running. Okay, so most of the new versions will have LDP as the default. Some of the different versions will have TDP as the default. Okay, so you can change that globally with the MPLS label protocol. So this should really be your first consideration when you are going to set up MPLS, is what is the label protocol I'm using? Okay, so once we choose the label protocol, we'll go ahead and enable it on the interface with the MPLS IP, and then verify adjacency with the show MPLS LDP neighbor output. Okay, now, in order to get this to work, this is assuming that we already have our IGP transport running. So we're either going to be running OSPF or IS to IS in the core typically. You could use other protocols, but 99% of the time you're going to be running either IS to IS or OSPF in the service provider core. They don't use the other protocols because they're not going to scale. Okay, no service provider network is going to route their network with RIP version 2 internally. Okay, it's going to be either OSPF or IS to IS. Okay, now there are some caveats of doing this this negotiation process. Okay, first thing, the label protocol is going to have to match. So if I'm running LDP and you're running TDP, we cannot be adjacent. Okay, we either both have to run LDP or we both have to run TDP. Now, just like in BGP, when you go to establish a peering session, you are going to be basing the peering on an update source that the iOS is choosing for you. With BGP, we know that the update source is going to be based on the outgoing interface in the routing table by default. Okay, so if I'm trying to get to the neighbor 1.2.3.4, I do a routing lookup and say, in order to get to 1.2.3.4, I'm going to use interface Ethernet 0. If we look at the IP address that's assigned to Ethernet 0, that's where I am going to source my packet from. Now, LDP and TDP, they are going to source the packets from the router ID. What this is going to imply is that the destination is going to need a route to the router ID in order for them to establish LDP or TDP adjacency. Okay, and the router ID is going to be chosen just like OSPF. We're going to look at our highest loopback address. If we don't have a loopback, then we're going to look at whatever the highest interface address is. Okay, so let's go ahead and bring up the command line here, and let's go ahead and enable basic LDP and TDP adjacency between the neighbors, and we'll look at how the TCP negotiation is going to work. Okay, so what I'm going to do here first is I'm going to finish building the IS to IS network, and we're going to get rid of our level 1 adjacencies, and we're going to do level 2 adjacencies. Okay, we want to make sure that everyone has a specific route for everything in the routing table. Okay, we'll go into more detail about this later. It has to do with how MPLS labels treat default routes when they are doing labeling. Okay, we want to get the specific routes in the routing table. So if we look at router 2 now, we can see it has a route to router 4, 5, and 6. It has a loopbacks of routers 4, 5, and 6. So on 6, let me go here, and under the IS-IS process, we'll say that the IS type is level 2. Okay, everyone is going to say the same thing. IS type level 2. Type level 2. Okay, so now if we look at the show CLNS IS-neighbor output, from router 5, we should see a level 2 adjacency with both router 4 and router 6, which we don't. Show CLNS IS neighbors. Let's say show. Let's make sure we have connectivity first off. Okay, we have connectivity to router 4 and to router 6. Go ahead and check that again. Show CLNS IS neighbors. Okay, so we have adjacency with router 4. A show run interface Ethernet 0.1. Okay, we're running. Oh, we have it on the interface. Okay, so what we saw here in global config, I set the level to be level 2, but then it was overridden by the interface level command circuit type level 1. Okay, so we'll just take this command off. No IS circuit type level 1. Okay, so now we're level 2 adjacent both with router 4 and router 6. Okay, if we go over to router 1, which is on the other side of the ATM cloud from router 2, it will run IS, define the net address, and on these interfaces, IP router IS. Okay, for the ATM, we're going to need to make sure we have CLNS transport. So we'll say protocol CLNS underscore IS broadcast. And under the process router IS, we'll say IS or IS type level 2. So we're only establishing level 2 adjacencies. And then lastly on router 3. So router IS net 490013. And now again, if you're running IS to IS in the exam, the net address is going to be arbitrary unless they are specifically assigning it to you. Okay, and keep in mind, this will control the level of adjacency. So if you want to be level 1 adjacent, you have to be in the same area as the remote device. So we'll say IS type level 2, and then on serial 12 IP router IS. Okay, so router 1 doesn't have, let's see, let me make sure it took that command. PVC 0102, protocol CLNS underscore IS broadcast. That's nice. All right, let's change, let's see, show version. Okay, so this is 7200 is running 12 to 25S. So you'll see on the higher level platforms, you'll see a lot of strange inconsistencies like this, where it'll take the command, but it's not applying it. So what I'm going to do here on the ATM interface, instead of running a manually resolved PVC on a multi-point interface, I'll just move this over to a point-to-point interface. Then resolution is not going to be a problem. So I'll say default interface ATM30. Then we'll create our new interface. It's going to be point-to-point. And typically, again, in service provider networks, you're not going to see a lot of multi-point configurations because they just don't make sense design-wise. Actually, let's try dot 10. Okay, so we have our IP address PVC0102, and then IP router ISIS. Okay, we'll go ahead and do the same thing on router 2. So default interface ATM30. Interface ATM30.10 is going to be a point-to-point link. IP address is 150.1.12.2. We're running ISIS and our PVC is 0201. Okay, so we have basic connectivity there. Let's say show CLNS IS-neighbors. Okay, so now we have reachability over the ATM. Okay, so if we go over to router 3, which is the opposite end of the network from router 6, and we show IP route ISIS, we should have reachability all the way over to router 6. Okay, which we do. Okay, so next step, once your IGB routing is enabled, we need to make sure that Ceph is enabled. So in global configuration, we'll say IP Ceph. Okay, then at the interface level to enable MPLS, we'll say MPLS IP. And we can see in this version, it took the command as MPLS IP, but it changed it to tag switching IP. Okay, if we look at the debug IP packet detail output, and really I should send this to the log, but I'm going to be risky. Let me write my configuration first. Do debug, let's see, debug IP packet detail. And not a whole lot of traffic going on, so it wasn't that much output. But we can see we are sending traffic to 225, 225, or 255, 255, 255, 255 with a UDP destination of 711. And this is telling us that based on this particular version, the default label protocol is tag distribution protocol. Because TDP is using UDP broadcast to port 711 in order to distribute labels. Now, if we go to the adjacent router, which is router 1, and we go to global config, we'll say IP Ceph, and on serial 2/1, we'll say MPLS IP. Okay, and in this case, it takes it as MPLS IP. And if we debug IP packet detail, we can see that we're sending traffic to the multicast address 224.0.0.2 with a UDP destination of 646. Okay, so now we have a problem. We have router 1, which is running label distribution protocol. We can see that based on that UDP port and the multicast address. And router 3 on the same segment, which is running tag distribution protocol to that UDP broadcast at port 711. Okay, so these neighbors are not going to be able to be adjacent. Now, the label distribution is only going to be locally significant between those particular neighbors. There's no restrictions on running LDP on some interfaces, running TDP on some interfaces, then using BGP and RSVP on different interfaces. And we'll see later when we get to complex inter-AS and carrier supporting carrier, we can be running a multitude of different label distribution protocols throughout the network. Okay, so as long as you're running the same protocol with your directly connected neighbor, you're going to be fine. Okay, so on router 1's interface here, let's go ahead and we will enable tag distribution protocol on the link over to router 3. Okay, so we'll go to interface serial 2/1, and we'll say MPLS label protocol TDP. And actually, before we do this, let's go ahead and say logging buffered, no logging console, and we'll debug IP packet detail. Okay, the IP packet detail output is going to show us what's going on the TCP relationship between these two neighbors. Okay, so if we go to the interface here, serial 2.1, and say MPLS label protocol TDP. Okay, there's a question here. What version is router 1 running? If we show run include iOS, this is a 72 or include image, not show run, show version. Show version include iOS. Okay, it's a 7200. It's running 12.2.25s. Okay, so it's basically one of the latest 12.2s trains. On router 3, show version include iOS. We're running 12.3T. Okay, so technically 12.3T is a later train than 12.2s, but it has an older default. So there's no really rhyme or reason to it. You just need to look at, you can either just statically configure it, go to global config and say, this is my label protocol, I know specifically what it is, or look at the default in by looking at the debug. I would highly recommend to manually set it, especially for any real implementation. Because if you change versions and your default label protocol changes, then that's going to be really bad. So if all your adjacencies go down between all your MPLS neighbors, then you're not going to be able to switch any traffic that's coming through you. So you would ideally want to put as many static options in there so you don't leave any of this up to chance. So if we go back to router 1 here and let's look at the show log output and see what's going on with that TCP adjacency. It's actually not showing us any output for the TCP relationship. What we need to look at here, let me undebug. We'll clear the log, and we're going to look at debug MPLS LDP say transport events, then show log. Okay, there's one of the debugs that's going to show the specific error that's happening, but what the problem is, it says we received a TDP, a tag distribution hello, from the address 150.1.13.3. Its router ID is 150.1.3.3. This is the address that we are now trying to start a TCP session to. Okay, it's called the connect source for the adjacency. But the problem is, if we look on router 1 and we say show IP routes 150.1.3.3, we don't have a route to that destination. Okay, we don't have a route to that destination because we didn't advertise it into IS to IS yet. But LDP and TDP, they are picking that as the connect source because that's what the router ID is. Okay, router ID is going to be the highest loopback by default. Now we can manually change the connect source, or actually the transport address it's called. Connect source relates to MSDP. I always get those two confused. We could go to the interface here and say on serial 2.1 that the MPLS LDP discovery transport address is something different. So this is basically like the update source command in BGP. So where am I going to source those updates from? Okay, now typically you're going to have at least one routable address on each device in the service provider network. A lot of times what you'll see is that service providers will use transit links that are unnumbered or transit links that use private addressing, because no one outside of the service provider network should be sending traffic to the actual link itself. Okay, but a lot of the times they'll do that and then use one publicly routable loopback that'll be /32, and they can use that for any type of communication that needs to go to the device. Okay, so we could change the transport address here, or alternatively just go to the loopback and enable the process, enable the IS process. Okay, so we can see we get the message now. We have a TDP neighbor which is up. Now if we look at the show MPLS LDP neighbor output, we're going to see two different things here. We have the peer's identification and the TCP connection. Technically, the router ID and the transport address are going to be two separate things. They are the same by default, but you can manually change them to be different with that transport address, the LDP discovery transport address on the interface. So the router ID is always going to be based on the highest loopback address, unless you manually change it. And the transport address is going to be the same as whatever the router ID is. So the problem we were seeing here is that router 1 and router 3 did not have routes to each other's loopbacks. In those broadcast UDP packets, they were telling each other, router 1 was saying to router 3, if you want to establish a TCP session to me, you need to send the packets to this address. And likewise, router 3 was saying, if you're going to send a TCP packet to me, you need to send it to this address. But when they do the routing lookup, they see that they didn't have that route installed, so they were not initiating the TCP negotiation. Okay, based on this output, you can also tell who is the TCP server and who is the client. Okay, the client always initiates the connection to the server at the well-known port. Okay, so we can see that router 1 is using port 711, where router 3 is using a randomly negotiated port between the two of them. So if we go back to router 1 here, we'll say undebug all, clear the log, and debug IP packet detail. Okay, if we look at the log now, we should see the TCP transaction between the two of them. Okay, so we can see packets are coming from 150.1.3.3 going to 150.1.1.1. So this is router 3's TDP router ID going to router 1's TDP router ID. Destination is TC port 711. So this means that router 1 is the server and router 3 is the client. Router 3 is the one that initiated the connection. Okay, so first off, you need to make sure that you have the basic transport for the neighbors. So are they directly connected? Do they have a route to the address that they're using for transport? If we didn't want to advertise the loopbacks between the neighbors, we could have gone to the interfaces here and said that our MPLS LDP discovery transport address is just going to be the address that's assigned to the interface. Okay, this would make it behave like BGP, where we're using whatever the IP address is on the directly connected interface. Actually, I don't need to clear the neighbor, it does it automatically. If we say show MPLS LDP neighbor now, after it comes back up, we can see that the peer ident, so the router ID, router 1's router ID is still the loopback, but now we can see the TCP connection is between the directly connected interface between them. Okay, so router 1 is sourcing it from 13.3, which is the serial address. Router 3 is sourcing it from 13.1 and then 13.3. Okay, so if you see a problem with the LDP or TDP adjacency, you need to look at what are the local interfaces that are assigned to the device, and do they have routing information for those? Okay, now in a lab type scenario, they could trip you up in a manner like this. Let's say that we go on router 1, and some later task in the exam, it says create a new loopback that has the IP address 160 dot whatever. If we did this and the LDP session reset, it would change its router ID to that higher address. And if the neighbors do not have a route to this address, then they are not going to be able to establish LDP or TDP adjacency to them. Okay, so as a general rule, you would want to go ahead and set your LDP router ID and make sure that they have, that all of the devices that you're going to run LDP with, that they have a route to that destination. It's only going to be locally significant between you and those neighbors. Okay, so let's go to router 3 here. Actually, let me undebug on router 1. Then we'll say show IP route IS to IS. Okay, so we have the loopbacks of routers 1, 2, 4, 5, and 6. And we have router 3 as well. Okay, so end to end, everyone should have a route to each other's loopbacks. Okay, we need to make sure this is the case because when we enable LDP, that is what the router ID is going to be based off of. Okay, so let's go ahead and enable LDP everywhere in the path, and then we'll take a look at what happens with the label to IP version 4 mapping. Okay, so on, let's see, on router 1, we have the ATM link over to router 2, so we'll say MPLS IP. Okay, and on everybody, we'll say in global config so everyone matches, we'll say MPLS label protocol is TDP. Okay, whether we're using TDP or LDP, it's not going to make any difference. They're both accomplishing the same goal. So on router 2, we'll say globally MPLS label protocol TDP. Then on the ATM, actually that should have been the sub interface on router 1, MPLS IP. Okay, so MPLS should be enabled on whatever interface you have the IP version 4 address associated with. So on router 4, the same thing, global config, MPLS, label, protocol, TDP. Okay, so once we enable it on the interfaces, next thing we're going to take a look at is to make sure that we have all of the adjacencies. So we'll say show MPLS LDP neighbors. We can see we have the adjacency with router 5. We can also look at the show MPLS LDP interface, or show MPLS interface. So we can see on gigabit 00 we have TDP running. On router 5, if we show MPLS LDP neighbors, we should be adjacent with routers 4 and 6, okay, which we are. Then on 2, we should be adjacent with 1 and 4. And then 3 should be adjacent with 1. Okay, there's a question here. In TDP, why would you still see the UDP broadcast even after the TCP neighbors are established? Okay, it's using the UDP broadcast as a neighbor discovery mechanism. So if a new neighbor comes onto the segment, let's say it's an Ethernet segment, Ethernet VLAN. So if a new router is installed on the segment, it's all automatic in the configuration. So all you have to do is enable the protocol on the interface. They're automatically going to discover each other through UDP. Then they're going to send the unicast TCP packets between each other to establish adjacencies. Okay, so if you have 3 neighbors on the segments, you're going to have 3 different TCP adjacencies. But you're still going to be sending the UDP packets out in order to see if anyone new came onto the segment. Okay, so once we have the adjacencies up, the next thing we're going to look at is the show MPLS forwarding table output. Okay, the forwarding table is going to show us our IP version 4 to label mapping. Okay, so this is showing us our IP version 4 to label mapping. So we can see we have local labels here. These are the label values that we are going to receive. Okay, so it means that, let's say a packet comes in with the tag 16, with the label 16. It means that we are going to send it out serial 1/2 with a label of 20. Okay, so what this means is that a packet, if it comes in with a label 16, it's going towards 150.1.24.0. We're going to send it out serial 1/2 with a label of 20. Okay, we can see a couple of these, they say pop tag. These pop tag output here, so pop tag for 12.0 and 1.1, this is the penultimate hop popping operation, the PHP operation. Because if we look at what are the IP addresses that we see these for, we have these for the loopback of router 1 and then the 150.1.12.0 segment. Okay, both of these are connected to router 1. So when router 1 is advertising these routes to router 3, it's saying if you're sending a packet towards something that is directly connected to me, do not send it as MPLS labeled. Send it as a regular IP version 4 packet. So if we have a packet that comes in some interface with a label of 21, we're going to remove the label and send it as a regular IP version 4 packet out to whatever this destination is. Okay, now the label forwarding information base is going to be built on a hop-by-hop basis based on the IGP routing table. Okay, so if we say show IP route here, the entries in here are going to directly correspond with the interfaces that are running MPLS and the IGP routes that we have learned over interfaces running MPLS. Okay, so if the interface is not running MPLS, we are not going to send MPLS tagged packets out there, which makes sense. If we're routing IP version 4 with someone, we're not going to send them MPLS packets. They're expecting IP version 4 packets. So when we look at the forwarding table, if you correlate these two tables here, you're going to see that they're going to exactly match up. So for example, the 204 network. We do not have a label that corresponds to 204 because if we look at that interface, which is Ethernet 01, we do not have MPLS enabled on it. If we were to go ahead and say MPLS IP on there, it would be added to the label forwarding information base. Okay, but every router is going to be completely independent on their decision of what prefixes they are installing in the label forwarding information base. Okay, this is going to be important in our troubleshooting process because we're going to need to check this table on a hop-by-hop basis to make sure that everyone is building an end-to-end label switch path or an end-to-end LSP for a particular destination. Okay, so from router 3's perspective, our next hop in the network is router 1. So if we go to router 1, and we say show MPLS forwarding table, okay, we see that if we are sending a packet out to router 3's loopback, we are not going to send it as tagged because router 3 is advertising the implicit null label onto us. So as traffic is going to router 3's loopback, Router 1 is performing the PHP, the penultimate hop popping. Because router 3 is saying, this destination is directly connected to me, so if you send me a label packet, I'm just going to have to remove the label and look at the IP version 4 destination anyways. So send it just as an unlabeled IP version 4 packet. Okay, and this is based on the label disposition process. So when we see pop label, that is the disposition. So we're taking whatever the top label is in the stack, and we are removing it from the stack. Okay, but only if the incoming label was 23. Now, if we look at this as we trace it throughout the network, router 1 is saying if a label comes in as 23, it should be going to router 3's loopback. We're going to remove the label from it. If we go one more hop away, if we go down to router 2 and say show MPLS forwarding table, and we look at the entry for router 3's loopback, router 2 says the outgoing label is 23. Now the label distribution happens from the source, actually from the destination away from the destination. It's the source of the routing advertisement, but it's the destination for the traffic. Okay, so router 3 is originating its own advertisement for its directly connected link. It's telling router 1, do not send me labeled traffic for that. Router 1 is saying, if I'm going to get to router 3's loopback, I'm going to use label 23. Router 1 turns around and says to router 2, if you want to get to this destination, you need to use label 23, because that's what I have installed in my label forwarding information base. So if we look at router 2, we can see the outgoing label is 23. The incoming label is 17. The next top router in the path is router 4. So if we go to router 4 and say show MPLS forwarding table, we can see that the outgoing label for router 3 is 17. So we can see on a hop-by-hop basis, we are swapping, or we are either imposing, which is pushing a label, we are swapping the labels, or we are popping them, which is disposing them. So router 4 is saying, take the packet, send it out 17 out the Ethernet. If router 2 received it in the Ethernet with 17, we're sending it out 23 out the ATM interface. If router 1 receives it in 23 in the ATM interface, we're going to send it out the serial interface with no label. Okay, so we can see on a hop-by-hop basis, they are building the end-to-end label switch path for this particular destination, which is router 3's loopback. If we go one more hop away, if we go down to router 5, we should see, when we say show MPLS forwarding table, if router 4 says the incoming label is 18, this must be the outgoing label on router 5 in order for this to be an end-to-end LSP. And we can see that it is. So router 5 is using 18 as its outgoing label, 19 as its incoming label. When we go to router 6, show MPLS forwarding table, we should see 19 as the outgoing label, which it is. Okay, so a lot of the time that we're debugging this week and that we're doing verification, you're going to see it's going to directly relate to this MPLS forwarding table. So right now, this is showing us, based on our IGP routes in the network, what are the labels that we are building based on them. Okay, so from router 6, let's say we go ahead and send some traffic to this destination. Okay, we'll ping 150.1.3.3. Now, when we send this, we are going to impose the label 19 and send it out gigabit 0/0. Okay, so let's go to router 5. We'll say debug MPLS packets. We'll go ahead and do this ping from router 6, and then we'll quickly go back to router 5 to look at its debug output. Okay, so if we look at router 5, it's saying inbound on Ethernet 0/1, we received an MPLS packet. The MPLS label was 19. We did a lookup in the forwarding information base. We saw that the outgoing label should be 18, and it should have been forwarded out serial 0/1. Or serial 0/0, actually. Okay, so if we go ahead and correlate this, if we say show MPLS forwarding table for 150.1.3.3, we can see it's saying if it came in with 19, which it did, we should have sent it out 18 out serial 0/0. Okay, now in this case, we are not receiving the reply. We are just seeing the one-way traffic going from 6 to 3. Now the reason why is that if we take, let's go ahead and take a look back at the diagram here. Okay, router 3 is advertising its loopback into IGP. This advertisement goes out to router 1, 1 passes it to 5, 5 passes it to 6. Okay, 6, when it was sourcing the traffic from, or when it was sending traffic to router 3, it's going to use the outgoing interface in the routing table. The outgoing interface in the routing table is this Ethernet link. Okay, this is advertised through IGP to router 5. 5 is advertising it to 1. 1 is advertising it to 3. So when we are looking at the traffic here, we are actually looking at two unidirectional label switch paths. Okay, they're end-to-end LSPs, but they are unidirectional. So traffic going from router 6 to 3 is going to use a different label switch path than the traffic going from 3 to 6. Now, the reason we didn't see the replies going through router 5 is that when 6 advertises the destination to 5, it is sending them with implicit null. Because this Ethernet between router 5 and 6, this is directly connected between them. When router 5 advertises it to 1, router 5 is also advertising implicit null. Because the Ethernet link between router 5 and 6 is directly connected to router 5. Router 1 is going to advertise some label value, some non-null label value. So when we look at the actual traffic flow, what we're going to see is that 3 is going to send a label packet to 1. 1 is going to perform the PHP operation, the penultimate hop popping. It's going to be sent over to router 5 as a regular IP version 4 packet. So this is the reason when we did the debug MPLS packet output, we only saw the unidirectional traffic flow. So this is very important in your troubleshooting process to think about, am I looking at an IP version 4 packet or am I looking at an MPLS labeled packet? Because you cannot do debugs you cannot do IP debugs on MPLS packets, and likewise you cannot do MPLS debugs on IP packets. Okay, so if we go to router 5 and we say debug IP packet, we will see those replies coming from 3 going back to router 6. Okay, there's a question here. So if router 6 doesn't have the loopback for router 3 in its routing table, how would it know what the next hop is, and how would it know what the label is? Okay, if router 6 did not have router 3's loopback in the routing table, it would not be able to build a label switch path for it. Okay, you can only build LSPs for routes that you have installed in the routing table. For LDP and TDP, this specifically means IGP learned routes. So if we were routing this network solely with BGP, we would not build any labels running LDP or running TDP. It would have to be IGP learned. In this case, our interior gateway protocol is, or IGP is IS to IS. Actually, our diagram's a little bit different than this. Let me shut down those ATM links, and we'll use the link between router 1 and 5. Okay, so we should see router 1 and router 5 directly adjacent here. Okay, so we see the IS-to-IS adjacency came up, and then the TDP adjacency automatically did. Okay, so let's say show MPLS forwarding table. So we can see now if we're sending traffic to router 3, we're sending it out the Ethernet towards router 1. Okay, these are the labels that we're going to use. We're going to use label 23 in order to reach that. Okay, now let's step back from this a bit and look at what happens when traffic is sent into the network from non-labeled destinations. Okay, so if we look at the diagram here, let's go ahead and introduce router 7 and router 8. Okay, we'll go ahead and introduce router 7 and router 8. Advertise their information into the IGP domain, but they are not going to be running MPLS. So they are going to be our customer edge routers, where router 3 and router 6 are going to be the provider edge routers. Okay, now in our particular case, these are catalyst switches, so they do not support IS-to-IS. So let's go ahead and we'll just run RIP on these links. So we'll run RIP between router 6 and router 8, and router 3 and router 7. Then we'll go ahead and do mutual redistribution on 3 and 6. Okay, so just the basic RIP process here. We're enabling the process. We're running version 2. We're not doing auto summarization, and then we're advertising the 10 network into the domain. So from router 7 here, we should have reachability to router 3, which we do. And then on router 8, we'll do the same thing. Okay, and we should have reachability to 10.168.6, which is router 6. Okay, so on router 3 and 6, we'll go ahead and run RIP as well, and then we'll do redistribution between RIP and IS-to-IS. So redistribute IS-to-IS, metric 1. Router IS-IS, we'll say redistribute RIP. Okay, so now we see we have an end-to-end path through the network there. So from router 8, we should have reachability to router 7, okay, which we do. And we'll go ahead and source this traffic off of our loopback. We'll say source is 10.1.8.8. Okay, so the traffic is successful. Now, if we go ahead and look into the provider edge routers, the first top provider edge router here is going to be router 6. And we'll say show MPLS forwarding table. Now we can see we have the entry for 10.1.8.0. Okay, this is the network that is being advertised by router 8 through RIP version 2. It says to reach that, we're going to go out gigabit 0/1. The traffic is going to be untagged. Now, an untagged packet is different than tag packet that is being popped. Because when you are popping a tag, it does not necessarily mean that you are removing the MPLS stack. It simply means that you are removing the topmost MPLS header from the stack. The MPLS stack simply means that you can have multiple tags on top of each other. When you're sending a packet as untagged, you are popping the entire stack, whether it's 1 label or 10 labels. And the reason why it's being sent as untagged is if we look at the interface here, show run gigabit 01, we're not running MPLS on the interface. Okay, so we can only send tagged packets out interfaces that are running MPLS. Okay, so what's going to happen here, the traffic is going to come in. It's coming in from 10.1.8.8. It's going to 10.1.7.0. We are sending it out as 27. Okay, so if we ping this, if we go ahead and ping that destination, actually what we'll do, let's go to everybody here. We'll say debug MPLS packets and logging buffered. No logging console. Okay, we'll go ahead and do this on everybody. Okay, so now everyone is debugging the MPLS packets to their buffer. So we'll go to router 8, and we'll send the traffic into the network. So if we look at router 6 and we show log, we see it was received in gigabit 00. The packets had a label of 26. We transmitted them out gigabit 01 without any labels. Now what we can see here is we're seeing actually the return traffic back from router 7 to router 8. We're not seeing the ICMP echo, we're seeing the ICMP echo reply. The reason why is when we receive the traffic, we are receiving it as a regular IP version 4 packet. So the debug MPLS packet output is not, that packet is not hitting that debug because it's not an MPLS packet. So if we look at the next hop, router 5, and we look at the log, we see we received it from router 6. We received it in Ethernet 01. It came in as 27. Then we sent it out Ethernet 0/0 as 27. So in this case, the incoming label and the outgoing label are the same. Then we go up to our next hop, router 1, show MPLS or show log. Let's try this again. We'll clear the log on router 1. Okay, so now the traffic is coming in fast Ethernet 1/0. Now you can see the output of this on the 7200s is a little bit different than the output on the 3600s and the 3800s. So some of the show commands will show you the difference, how to interpret them. There's some differences in when you look at the label forwarding information base. The 7200s do not show BGP labeled routes and VPN labeled routes by default. So when we get into MPLS VPNs in more detail tomorrow, we'll see why that is going to be significant. Okay, so we can see we're receiving it in the fast Ethernet interface. RX, we received it. We're transmitting it out serial 2/1 with a label of 28. What this is output is showing us the label, the class of service, and then the time to live. So when we do QoS later in the week, we can see that we can change this. This is the MPLS experimental bit here, or bits, 3 bits. And that is the time to live. So it's coming in as 27, we're sending it out as 28. Now we can verify this by looking at the show MPLS forwarding table for 10.1.7.0. What we should see is the incoming label is 27, the outgoing label is 28, which we do. It says incoming label 27, we're gonna swap it with 28, send it out serial 2/1. And that goes over to router 3. We show MPLS forwarding table, or show log. We can see that we received it in serial 1/2 with a label of 28. We transmitted it out the Ethernet without any label. So we are doing the label popping or disposition. Now in this particular case, we're not really gaining any functionality by running MPLS in the network. The reason why is that the routes that are being advertised by the customer edge are still being installed everywhere in the transit path of the network. So basically, just instead of sending routed IP packets, we're sending MPLS labeled packets. But we're not saving any resources. We're actually using more resources because we have not only our label, or not only our routing table and our CEF table, but now we also have the label forwarding table that we need to maintain on all 4 of these routers in the transit path. Now what the advantage is going to come into play is when we have an MPLS tunnel. Okay, and MPLS tunnels, these are going to be the basis of how the MPLS VPN logic works. Okay, so what we have here, router 7 is advertising routes to router 3. Okay, in this case in the diagram we're using eBGP, we're using RIP version 2 in the example, both of them are going to be the same. It's not going to make any difference. Okay, the route comes in as router 3 learns it however. It could learn it statically, it could learn it through BGP, or could learn it through IGP. It advertises it to router 6 via BGP. They're running iBGP. Router 3 is telling router 6, use my loopback address as the next hop value. Then router 6 advertises the route onto router 8. So we have an end-to-end routing advertisement between these 3 devices, or those 4 devices. So routers 1 and 5, they do not know about the routes from router 7. They do not know the routes from router 8. Now when the actual traffic comes in, what's going to happen is that a packet comes in, let's say packet is going to 10.1.8.8. It is received by router 3. Router 7 is sending it to router 3. The destination is 10.1.8.8. Router 3 does a lookup and sees that it is an MPLS labeled packet. Actually, it's not an MPLS labeled packet. It would be if it's a VPN. It sees it as it's going to see it as a BGP route. Okay, we'll see this on the command line. It's going to see it as a BGP route, and it needs to do the route recursion process. Okay, the reason why it needs to do route recursion is that router 3 and router 6 are not directly connected. Router 3 is going to say, in order to get to 10.1.8.8, I am going to use router 6's loopback, 150.1.6.6. But 150.1.6.6 is not directly connected, so now we need to do another routing lookup. But 150.1.6.6 is label switched because we're running IGP and LDP between these neighbors. So what is going to happen when router 3 receives it? It's going to take the IP version 4 packet, encapsulate it inside an MPLS header going towards the loopback of router 6. Because we know that any traffic going from router 7 to router 8 is going to have to pass through router 6. Okay, router 3 knows that based on the BGP next hop value that is being advertised. So instead of router 1 and 5 having to know everything in the transit path, they simply need to know how to get to the exit points. Okay, it's the same principle if we were using a GRE tunnel between router 3 and 6. Let's say we're using GRE and we were running BGP over the GRE tunnel. Router 1 and router 5, they would not need to know all of the final destinations. They would only need to know how to transport the GRE traffic between router 3 and router 6. Okay, so let's go ahead and take a look at this on the command line. So what we'll do, we're going to run BGP between router 3 and 6, and instead of redistributing RIP into IS to IS, we're going to redistribute RIP into BGP. So router 1 and router 5, they are not going to have the route again to router 7 or router 8. Okay, they're going to have it just to the internal routers. Okay, so on router 3, actually on everybody, let's undebug. There's a question here. How does router 3 know that 10.1.8.0 doesn't have a label assigned? What did it have to do because of the lookup? Or we'll take a look at this in a second, why it doesn't have a particular label. Okay, so we undebugged on 5 we're missing. Okay, so on router 6, we'll go ahead and run BGP. We're going to peer with router 3, remote AS1. Our update source is going to be our loopback. Okay, we're peering BGP between the loopbacks. Now we're going to redistribute RIP into BGP. We are not going to redistribute RIP into IS to IS. And we are going to redistribute BGP into RIP. Okay, so BGP or redistribution is happening between BGP and RIP instead of RIP and IS to IS. Okay, so we're peering with router 6. Redistribute RIP. Okay, so first off, let's check our BGP adjacency between these neighbors. Okay, so the adjacency is up. We're not learning anything from them yet, though. So let's see what we have installed locally. Show IPBGP. Okay, we have the routes learned from RIP. So right now we're in the process of convergence. We can tell this because these are not best routes as of yet. And now we can see we have the routes that were coming from router 7, plus we have the routes that were coming from router 8. Now we can see that for the loopback of router 8, this is not installed as a best path. And if we say show IP route 10.1.8.8, we have it installed Actually, now it is the best route. Okay. That was probably just converging. Let's show IPBGP again. Okay, now it's the best route. It says that it is reachable via 10.1.68.8. Okay, this is actually not what we want to have here. What we want to see is that it's reachable via router 6. Technically, this is going to work here. It's going to end up in an extra step in recursion. But what we really want to say under the BGP process is that for this neighbor, I want to be the next hop. Okay, router 6 is going to say the same thing. It says to get to 10.1.8.0, use 150.1.6.6. Now, if we look in the transit path, if we look at router 1, for example, show IP route 10.1.8.8, okay, we don't have a route to this because we're not running BGP, nor have we redistributed IS to IS into BGP. Here, what we want to see is that it's reachable via router 6. Technically, this is going to work here. It's going to end up in an extra step in recursion. But what we really want to say under the BGP process is that for this neighbor, I want to be the next hop. Okay, router 6 is going to say the same thing. The routes learn from RIP. So right now we're in the process of convergence. We can tell this because these are not best routes as of yet. And now we can see we have the routes that were coming from router 7, plus we have the routes that were coming from router 8. Now we can see that for the loopback of router 8, this is not installed as a best path. And if we say show IP route 10.1.8.8, we have it installed. Actually, now it is a best route. Okay, that was probably just converging. Let's show IPBGP again. Okay, now it's a best route. It says that it is reachable via 10.1.68.8. Okay, this is actually not what we want to have here. What we want to see is that it's reachable via router 6. Technically, this is going to work here. It's going to end up in an extra step in recursion. But what we really want to say under the BGP process is that for this neighbor, I want to be the next hop. Okay, router 6 is going to say the same thing. Okay, so if we look at the BGP table now, we can see it says router 3 says to get to 10.1.8.0, use 150.1.6.6. Now, if we look in the transit path, if we look at router 1, for example, show IP route 10.1.8.8, okay, we don't have a route to this because we're not running BGP, nor have we redistributed IS to IS into BGP. Or the other way around. We didn't redistribute BGP into IS to IS, or we didn't redistribute RIP into IS to IS. So the only thing the routers in the transit path know are about the endpoints of the network. So we know how to get to router 6, we know how to get to router 3. Then we know our other internal information. We know how to get to router 5, then we know about the link between router 5 and router 6. Now if we go to, let's go to router 7, and we'll ping 10.1.8.8 coming from 10.1.7.7. Actually, first off, let's make sure these guys have the routing information. Show IP route RIP. Okay, they don't have the routes coming. So on router 3, let's take a look at the running config. Okay, so we're learning the routes from router 6. We can see that based on the show IP BGP output. But if we look at the show IP RIP database output, these routes are not getting redistributed in. Okay, they should say via redistributed. And we can see in the configuration we do have the redistribute BGP command. What we are missing here is we need to disable the default behavior of the iOS. Okay, for loop prevention, it is not going to allow us to redistribute iBGP learned routes into IGP. So what we need to say under the BGP process here is BGP redistribute internal. So it says allow redistribution of iBGP learned route into IGP. Okay, normally you wouldn't want to do this because IGP has a lower administrative distance than BGP, so you would start routing through IGP instead of BGP, but that's actually what we want in this case. So we're going to say BGP redistribute internal, and we'll say this on router 6 as well. Okay, so now let's try to test connectivity, now that we have the routing information. Okay, so we do have connectivity. But what's going on is that router 1 and router 5, who are in the transit path, they neither have a route to the source, nor do they have a route to the destination. Okay, now let's go ahead and back to everybody, and we'll say debug MPLS packets on router 3, 1, 5, and 6. Okay, now there's a couple different types of traffic we are sending and receiving here. On router 1, it says traffic is coming in serial 2/1. It has a label of 19. We are sending it out as Ethernet 1/0 with a label of 17. Then we have traffic coming in the Ethernet with a label of 23. We are sending it out Actually, we don't see it sending out the serial because we're sending it out as an IP version 4 packet. Okay, we're receiving this as an MPLS packet. We're actually doing PHP here. So we're sending it out as an unlabeled packet. But if we look at the show MPLS forwarding table output, we need to figure out what is associated incoming 19 and outgoing as 17. We can see coming in as 19 and going out as 17, that's traffic going to router 6's loopback. We can see that there's a lot of bytes that are being switched between these two destinations. Okay, so let's go back up to router 7. And let's say repeat, we'll send 10,000 packets. If we look at router 1 and say show MPLS forwarding table, we're going to see that this counter is going to go up and up here. Because when router 1 receives the traffic, it does not actually know that it is traffic going between router 7 and router 8. The only thing that it sees, it's MPLS labeled traffic going to the loopback of router 6 or going to the loopback of router 3. And that is based on the routing lookup that router 3 and router 6 are performing. Okay, so the way it works is that router 3 says, I have an IP packet that came in. It's going to 10.1.8.8. 10.1.8.8 is known via BGP. The next hop is 150.1.6.6. We do a lookup on 150.1.6.6. We see this is known via IS to IS on serial 1/2. When we look at serial 1/2, we see this interface is running MPLS. So now we need to know, is there an MPLS label going out serial 1/2 that is associated with the BGP next hop value of this route, which is 150.1.6.6. So we say show MPLS forwarding table 150.1.6.6. And in this case, there is. It says if the traffic is going to 150.1.6.6 out serial 1/2, use an outgoing label of 19. So what we have here is that when the packets get into router 3, when the packets get into router 3, it is going to be receiving it as an IP version 4 packet. Okay, the IP version 4 packet, it's going to destination 10.1.8.8. It is going to impose an MPLS label onto the packet. This label is going to say, I'm using label 19. Because the next hop value is the BGP next hop value is towards a destination that we know via MPLS. So now when router 1 receives the packet, it's not looking at the IP version 4 destination. It's not looking that the destination is 10.1.8.8. It's saying, I see the incoming label as 19. So we look at the MPLS forwarding table, we see it comes in as 19. And if we look back at the command line, if we go to router 1, say show MPLS forwarding table 150.1.6.6, if it comes in as 19, send it out 17 towards router 5. Router 5 gets this, show MPLS forwarding table 150.1.6.6. It says, if it comes in 17, pop the tag, send it out Ethernet 0/1 towards router 6. So we can see router 3 is doing the label imposition. It is imposing 19. Router 1 is doing a swap operation. It's taking an incoming label of 19, swapping it with 17. Router 5 is doing penultimate hop popping. It's coming in as 17, it's popping the tag and sending it out to router 6. When router 6 receives the traffic, it does a regular IP routing lookup and says, I know about this final destination. I have it through IGP and it's reachable out gigabit 0/1. So we forwarded out that interface as a regular IP version 4 packet. So the advantage here we can see is that when we go to send traffic through the network, the devices in the network core do not need to know about the customer routes. Okay, the devices in the MPLS core do not need to know about the customer routes. The only thing that they need to know about is what is going on in the service provider network. So they need to know what is the route to router 6's loopback. What is the route to router 3's loopback? Okay, technically we could only exchange MPLS labels for those two routes if we wanted to. And we'll show that later in the week when we do label filtering. But we could say only exchange labels for the loopback of router 3 and of 6. Everything else will do regular IP version 4 routing. Okay, so when the lookup points to a BGP route, and the BGP next hop is a label switched path, then it is going to be tunneled through MPLS. Okay, but this principle is going to be based completely on the fact that we are running BGP between the provider edge routers. Okay, so we're going to see when we get into MPLS VPNs tomorrow, without BGP, it is not going to allow this feature. Okay, MPLS is dependent on IGP for label distribution, then it is dependent on BGP for its tunneling mechanism to do its routing lookups. Okay, technically you can do MPLS without using LDP, TDP, or RSVP. You can do it just with BGP. But the most common setup you would see is this, where inside your internal transit network you're running IGP and either label distribution protocol or tag distribution protocol. And then between the provider edge routers, they are exchanging routes with BGP. Okay, there's a lot of different complex setups that we can do with route reflection and confederation in order to exchange the BGP information, and we'll take a look at that more in detail tomorrow when we get to more information about VPNs. Okay, let's see, there's a question here. When router 6 receives an MPLS packet that contains no label, is there a bit to tell it to use the IP version 4 lookup? How does it take an MPLS packet coming and know to use IP version 4 routing to switch it? Okay, let's look at the debug output on router 5. A router 5, when the traffic is going from router 7 to router 8, router 5 is the one that is going to do the PHP operation. It is popping the label as it's going out to router 6. Okay, so on router 5, let's say on Ethernet Ethernet 00, we're going to say no IP route cache. And on Ethernet 01, no IP route cache. Okay, the reason we're doing this is because we need to debug traffic that is transiting through the router. By default, you can only debug traffic that is process switched, IP traffic that is. If it is CEP switched or fast switched, you cannot debug it. It has to be process switched. Traffic that is destined to the router is always going to be process switched. So what that means, by default, you can only debug traffic that is going to the router. Okay, so in this case, we're disabling route caching. It's going to allow us to debug traffic that is moving between the interfaces. So we'll clear the log here. We'll say debug IP packet. Actually, to filter through this a little bit, let's say access list 100 is going to be just ICMP traffic. Then we'll debug IP packet detail and use access list 100 to filter the output. Okay, we're also debugging MPLS packets. Okay, so we still have reachability from router 7 to router 8. Now if we look at the output on router 5, show log, we can see that we received a packet coming in Ethernet 0/0. This is the link to router 1. It was an MPLS packet. It had a label of 17. We switched it to Ethernet 0/1 and we are transmitting it with no label. Once the label disposition happens, it is sent down to the IP process. So we can see that router 5 now sees it as a packet coming from 10.1.7.7 going to 10.1.8.8. But router 5 does not have a route to 10.1.8.8. That's okay because the MPLS forwarding table already switched it to the outgoing interface. So router 5 knows that this traffic is going towards 150.1.56.6. And this is based on the forwarding table. If we say show MPLS forwarding table towards 150.1.6.6, the incoming label is 17, which we saw that the packet came in as 17. It's going towards the loopback of router 6. The destination is not actually the loopback. It's just going towards that loopback. We're going to send it out Ethernet 01 with no tag. We're going to use the layer 2 address that is associated with this next hop. So the MPLS process switches the traffic between interfaces. Then we're encapsulating it towards that address. Okay, so technically when router 6 receives this packet, if we go to router 6 and we'll do the same thing. We'll say access list 100 permit ICMP any. Then debug IP packet detail 100. Okay, when we send the ping, then we look at, actually let me clear the log. Right now, 6 can't see it because it's transit traffic. Let me say no IP route cache. And we'll try this again. So we see when router 6 receives it, it's coming in gigabit 00. This is the interface pointing towards router 5. It's just a regular IP version 4 packet. So the penultimate popping process is just an optimization to make router 6 not have to do both the label lookup and the IP version 4 lookup. Because on router 5, it's the MPLS process that is making the forwarding decision, saying it's coming in Ethernet 00 from router 1, sending it out Ethernet 0/1. A router 5 is not performing an IP version 4 lookup. It's performing only a label lookup. When router 6 receives it, it is an unlabeled packet. It's a regular IP version 4 packet. So router 6 only performs an IP version 4 lookup. So without penultimate hop popping, router 6 would receive the label packet, look in the label table, and it would say, I need to dispose the label, so take the label off, send it to the IP process, do another lookup, then forward it out the interface. So you can do that. It's just going to be it's just going to be not as optimal forwarding on router 6 because you're going to have to do 2 different lookups on it. Okay, so this logic of the tunneling between the neighbors that we see here, this is going to be the basis for all of the other advanced features that are going to be based on MPLS. Okay, so the basic logic is that by adding the MPLS header onto the packet, we are tunneling it through the service provider network, and the service provider network does not care what it is. Okay, the payload can be IP version 4. It can be a frame relay packet. It can be an ATM cell. So a lot of different things that we can encapsulate inside of MPLS. We'll talk about a little bit later in the week any transport over MPLS, which is encapsulating stuff like ATM and Ethernet over MPLS. But based on the versions that they're using in the lab, it's going to be unlikely to see that stuff. It's good to know what it is, but once you build the MPLS network, the configuration on the PE routers is going to be pretty straightforward. Okay, so you could basically take the documentation example, plug it in, and you're going to be good to go, assuming that your MPLS network is built. Okay, the last thing that I want to talk about today here real quick is the cell mode MPLS operation. Okay, what we looked at so far is called frame mode MPLS. Basically, frame mode MPLS is just any MPLS that's not running over an ATM interface. Okay, you technically can run frame mode MPLS over ATM, which is what we were doing earlier, when you are running it over PVCs. Okay, when MPLS was starting to get popular, one of the things the service providers were concerned about is they had all this ATM infrastructure, and now they have an IP network that is running on top of it. So not only would they have to provision the ATM PVCs, but then you would have the extra protocols running on top of it. You would have your IP header encapsulated inside MPLS, then re-encapsulated inside ATM. So it was a lot of additional provisioning that they would have to do getting these two networks to work together. So they came out with this notion of cell mode MPLS, which says that we are going to use the ATM VPI and VCI values instead of our MPLS labels. So the ATM switches, they're called ATM label switch routers. So they're basically IP and MPLS enabled ATM routers are going to communicate with their IP enabled ATM switches. Okay, for example, the LS1010 that we have, you can configure IP routing on it, and it's going to be an MPLS aware ATM switch. So the ATM switches talk to the ATM routers, and they dynamically negotiate what VPI and VCI numbers to use for traffic that is transiting the devices. Okay, so it allows for the flexibility of MPLS where you don't have to do any manual provisioning, but we don't have extra overhead because we're encapsulating the cell or the traffic right into the ATM cell, but we're using the VPI and VCI value instead of the MPLS header. The configuration is pretty straightforward, and it depends on the ATM switch being MPLS aware. Okay, so the previous example we looked at, we were doing a basic PVC configuration between router 1 and router 2. Okay, so what I'll do here, let me bring up the LS1010 configuration, and we'll enable cell mode MPLS on the LS1010, then we'll configure it on the routers to talk to the switch as well. And now in the CCI lab exam, you're not going to be dealing with the ATM switch, you're going to be dealing with just the routers. So if you were to get cell mode MPLS, then you would be dealing with just the label edge routers, okay, which would be router 1 and router 2 in this case. They would be label edge routers. Okay, so we'll get rid of the configuration on router 1 and 2 for ATM. And then we'll go to the LS1010 here. And if we take a look at the configuration here, we have OSPF enabled and we have IS-to-IS enabled. Okay, so we're saying just run OSPF on any interface that has IP, and we have IS-to-IS enabled. We have the net address defined there. Okay, so what we're going to do here, the interfaces that we have are ATM 001 and 000. Okay, so these connect to router 1 and router 2. So we can see right now we have just a basic PVC configuration. So it's saying if a packet comes, if anything comes in from router 2 using VPI VCI 0/201, send it out ATM 000 with a VPI of 0 and a VCI of 102. Okay, so we're switching to ATM cells based on that VPI and VCI value. So on ATM 001, we're going to get rid of this. And instead, we're going to replace this with a regular routing configuration. So we're going to say on the connection to router 1, we'll have an IP address 150.119.9/24. Okay, we're going to run IS-to-IS. We're going to run MPLS, tag switching IP. Okay, additionally, we're going to change the control VC number. Okay, the default virtual path identifier and virtual channel identifier for cell mode MPLS is 032. Okay, we'll change it to 164 on this link. Okay, it's only locally significant to that particular link. Okay, now on the connection over to router 2, we'll say IP address 150.129.9/24. We're running IS-to-IS, and we're running MPLS, tag switching IP. Okay, now on router 1 and router 2, we're going to create new subinterfaces that are going to attach to the ATM cloud, and these are going to be MPLS subinterfaces. Say .12 MPLS. Our IP address is 150.1.19.1. We're running MPLS, tag switching, or MPLS IP. And in this case, our, let's see, MPLS ATM, yeah, MPLS ATM control VC is 164. In router 2, we're going to do the same thing. Interface ATM 3/0.2 is an MPLS subinterface. IP address is 150.1.29.2/24. We're running MPLS, and we're running IS-to-IS. Uh, 12. IP router IS-to-IS. Okay, so let me bring up the other interfaces in the transit path here. On router 1, we'll shut down the link over to router 5. And on router 5, we'll bring the link back up to router 4. Okay, so now, let's see, 4 has the information about, all right, let's take a look at router 2, and we'll show CLNS IS neighbors. we can see that we're running IS to IS with router 4, but we're also adjacent with the LS1010 over our ATM subinterface. If we look at the show MPLS LDP interface output, or show MPLS interface, we are running, oh, let's see, I may not have enabled it. Show MPLS LDP neighbor. The output is a little bit different on the 7200. So we can see that on the ATM interface, we are adjacent with the LS1010. If we look at the show MPLS forwarding table output, we can see that we are learning the route 150.1.9.9 through the LS1010's interface. It says if it comes in 21, so if we have an incoming label 21, send it out to the ATM cloud, but use the VPI VCI 1/33. Okay, so instead of using an MPLS label, we're using the VPI and VCI to dynamically determine where it's going to go through the ATM network. So essentially, if we had tons of ATM switches and we enabled cell mode MPLS on all of them, it would be automatically a full mesh of all the virtual circuits, and based on the MPLS labels, we would be determining where it is being switched throughout the network. Now, router 1 is not adjacent here. Let's say show MPLS LDP neighbor. Okay, we don't have the connection to that router. Show run interface ATM 30. Now it's shut down. No shut. Okay, so now we can see we're adjacent with the LS1010. If we say show IP route IS to IS, we can see we're learning the route from router 3 in the serial link, and we have the rest of the routes learned in the ATM link. So if we look at the show MPLS forwarding table output, we can see that we're using different VPI and VCI values for traffic going out to the ATM cloud. Okay, so it's pretty much automatic. You just need to enable. If we look at show run, let's just show run. Okay, so we create a sub interface for MPLS. We're running IP on it. We're either going to be routing OSPF or IS to IS because those are going to be our core network protocols. Then we enable the control VC. A control VC is going to be 032 by default. We didn't need to do this on router 2 because on the LS1010 we didn't change it on router 2's connection. So if we go to router 2 and say show ATM virtual circuit, we could see we have PVC 032 as a permanent virtual circuit. The rest of them are labeled virtual circuits. If we look on router 1, do the same thing, show ATM virtual circuit. We have 164 is our PVC, that's our control PVC. The rest of these are labeled virtual circuits that they were negotiated through MPLS. So if we go to router 7 now, we should still have connectivity here, and this traffic is actually going to be transiting to LS1010. Okay, if we look at the LS1010, and we show, let's see, show ATM. Okay, so if we look at the show MPLS ATM LDP bindings on the LS1010, we can see based on these specific IP routes what the interfaces are and what the virtual circuits are going to be. So this is depending on, if we look at the LS1010, if we show IP route, this is depending on them participating in the routing domain. So if we have ATM switches that are only layer 2 aware, then they would not be able to participate in the MPLS domain. But in this particular case, the ATM switch processor in the LS1010 is layer 3 aware, so it can run MPLS with the rest of the routers in the network. Okay, the last thing I want to cover here is, I mentioned it briefly before, but the reason why it is important to use the loopback of router 3 and router 6 when they are peering BGP. Okay, let's go ahead and right now we see that we have connectivity between router 7 and router 8. Okay, let's go ahead and change the BGP peering between router 3 and 6. And instead of using the loopbacks, let's use the serial interface on router 3 and the Ethernet interface on router 6. Okay, so their outgoing interface is towards the router, or towards the rest of the service provider domain. So when 3 peers with 6, we're going to have a peer with this interface, and when 6 peers with 3, we're going to have a peer with that interface. Okay, so let's go over to router 3. We'll get rid of the neighbor to router 6, and we'll replace this with 56.6. And we'll say next hop self. And likewise on router 6. So first thing we'll say, show IP-BGP summary to check our peering. Okay, we're peering with router 3. If we say show IP-BGP, okay, we see we are receiving the routes. So let's go over to router 8 and show IP route. Okay, we see those routes are through RIP. We take a look on router 7, show IP route. Okay, we still have the routing information, so let's go ahead and try testing connectivity. Okay, so we can see it's failing. Let's go ahead, we'll leave this running. Okay, we'll leave this running, and then we'll go ahead and do some debugging through the network. Now, from router 3's perspective, it is receiving an unlabeled IP version 4 packet coming in from router 7. Okay, if we say show IP route 10.1.8.8. Okay, the packet comes in, the destination is 10.1.8.8. It says it's known via BGP. The BGP next hop is 150.1.56.6. We can see that the interface that this is reachable out, if we say show IP route 150.1.56.6, serial 1/2 is running MPLS. So now we need to look in the forwarding table, do we have an entry for this next hop? So we'll say show MPLS forwarding table 150.1.56.6. We do have an entry. It says the outgoing label is 22. So we send it out serial 1/2 over to router 1. Okay, router 1 gets it. If we say show MPLS forwarding table 150.1.56.6. Okay, we can see that we're saying if it comes in with a label 22, send it out to the ATM cloud, use VPI VCI 1/42. Okay, so it transits the ATM cloud, it gets back out to router 2. It comes in as 20, it's going out as 23 over to router 4. Router 4 receives it as 23. It says pop the tag and send it out to router 5. When router 5 receives it, what type of packet is router 5 going to receive it as? In this case, router 4 is doing the PHP. Router 4 is popping the tag and then sending it out to router 5. If we get to router 5, it is going to receive it as a regular unlabeled IP version 4 packet. So if we say do show debug, we're debugging IP packet detail. So let's say clear log and show log. Okay, that traffic is still running. Router 5 is now seeing it as an IP version 4 packet, and it says we do not have a route to that destination. The traffic is unroutable. We now try to go and respond with an ICMP unreachable message. We're sourcing it from ourselves, going back to the source, which is router 7. But we don't have a route back to the source, so the ICMP unreachable is also unroutable. So now what's happening is that router 5 is black holing the traffic. Okay, let's take a look back at the diagram here. Now when router 3 sees the next hop of this route from router 6, it's saying use the next hop 150.1.56.6. This is learned via IS to IS, which is our IGP. Here, our network actually looks like this because we're trending to ATM cloud as well. Okay, so router 6 is advertising that link out. It's advertising it out through IGP. Router 5 is also advertising it through IGP. It's advertising it to router 4 as an IS to IS route, and it is also advertising an MPLS label. Now, what label is router 5 going to be advertising? Since this prefix is directly connected, router 5 is going to be advertising implicit null. So router 5 is telling router 4, this destination is directly connected to me. Do not send me labeled packets for this destination. Because if you send me an MPLS labeled packet, I'm just going to have to dispose whatever label is on there and then do an IP version 4 lookup. So I don't want to do 2 lookups. I want to do just the regular IP version 4 lookup. So what's happening is that the traffic is going from 7 to 3. It's getting labeled inside of MPLS. 3 is sending it to 1, 1 down to 2, 2 over to 4. When 4 gets it as a labeled packet, it is popping the label and sending it out to router 5 as a regular IP version 4 packet. But the problem is, router 5 does not have a route to the final destination, which is the 10.1.8.0. And the reason this happened is because router 3 and router 6 were peering based on that Ethernet link. Okay, this is only an issue because that Ethernet link is also directly connected to router 5. If the Ethernet link was not connected to router 5, then it would not be advertising implicit null for the destination. Okay, so by peering between the loopbacks of 3 and 6, we're ensuring that router 4 does not perform the PHP, but instead router 5 performs the PHP. Because when router 5 looks at it, it says this destination, router 6's loopback, is not directly attached to me. So I will not advertise implicit null for it. When router 6 advertises it, it is directly connected, so it's going to advertise implicit null to router 5. And that's the case that we had before. So router 5 was receiving the labeled packet. It was popping the label and sending the IP version 4 packet out to router 6. But now in this case, that process is happening on router 4, which is one hop not far enough into the network. That operation really should be happening on router 5. Okay, so like Brian was talking about earlier, the service provider lab, you need to make sure that you are properly designing your network before you make these decisions in at the lab time. Because you could go ahead and do your BGP peerings, and then 3 hours later you get to some situation like this, you realize that you have to take all your BGP configuration off and start it again using a different address. Okay, that's going to be a lot of wasted time in your configuration. So try to look at these issues beforehand, and really any examples that you see with MPLS will use the loopback for the peering, but they don't really explain why you would use that as opposed to the interface. But if you use the interface, you're going to see it's not going to work, and that's because of this PHP that's happening on the device. Okay, so the commands we saw again, the show MPLS LDP interface, that's going to show you what protocol you have on the interface. So do you have TDP or do you have LDP on the interface? Show MPLS LDP neighbor, that should be the first thing you check once you enable MPLS on your local device and the remote device. Okay, make sure that the adjacency is there. If it's not coming up, then you need to look at, do I have a route to whatever their transport address is? By default, the transport address is going to be the router ID, which is typically their loopback. If you see somewhere in the exam that they're asking you to add additional loopback addresses, that should be an indication that this could cause a possible problem. So if you add, it's kind of like in OSPF with the virtual links. If you add a different router ID, or your router ID changes later, you can break some portions of the network that were working properly in the beginning of the exam. So if they wanted to be mean, they would wait until the last possible task and then tell you to add a new address, and then it breaks your whole MPLS network. Okay, then for the actual forwarding table, we're going to look at the MPLS forwarding table. You also need to correlate this with the IP routing table on the router that is doing the imposition. So the provider edge router, you're going to look at the IP routing table in addition to the MPLS forwarding table. Okay, we'll look at tomorrow when we look